Kia ora, we're doing page 71. It's just going to be a full walkthrough. I haven't looked at the question beforehand, so you can sort of see my thinking process along the way. The distance in meters travelled by a train from a station is given by the relationship S equals 2t squared minus t cubed over 9, where t stands for time in seconds. Okay, cool. So we're in meters, we're in seconds. Distance, that's convenient that that's an S, because just remember they're saying distance, but this is going to work by displacement as well, I think. Okay, how far has it travelled after 2 seconds? So this formula is already talking about distance travelled, so we can easily just substitute 2 in for the time, and it should give us our answer. So the distance, which is by S, is 2 times 2 squared minus 2 to the power 3 over 9. We're going to do that in our head. We'll use our calculator for that, I think. Here's the best place for the calculator, maybe over here today. We'll go right there. Okay, so let's type that in. So it's going to be 2 squared minus, we're going to have to be a little bit careful with this, 2 to the power 3, and I'm going to have to do that in brackets actually. Oh, I could have done divide. Oh, it's all good. Will that do bed mass? Yes, it will. 7.1. We'll go 3 dp today. Oh, no, it's in meters. I'll go 2 dp. 7.11 meters. Does that make sense for 2 seconds travel time? Yeah, I think that makes a bit of sense. Let me double check it. 8 over 9, that's going to be around about 488 minus something. Yep. How fast is it traveling after 2 seconds? How fast? Okay, so we start off with distance. So with kinematics, we've got to remember that we get S of t, which is displacement, then that differentiates down to our velocity in regard to time, and then that differentiates down to our acceleration in regard to time. And then we also know that we can anti-differentiate to get our reverses. But we started off with the displacement, right? So that means we're only ever going to really have to do differentiation. They'll either start you off, if they start you off with displacement, you're only going to need to do differentiation. Right, if they start you off with acceleration, you're only going to need to do anti-differentiation. So yeah, here displacement, so we just have to differentiate. So let's do that with this, and we'll go, I'm going to call it V in regard to t. I'm going to do my notation because I prefer it. And then we'll differentiate here. Okay, so we multiply by the power for t minus, and then we multiply by the power, that's going to make it over 3 instead of over 9, and then it's going to be t squared. Are we happy with that? Yep, looks pretty good. Okay, and then so let's do that after 2 seconds. So it's at 2 seconds, 4 times 2 minus 2 squared over 3. We'll get our calculator again. We can go, we'll be a little bit lazy. 8 minus 2 squared is 4 over 3. 3 over 3, I think they want their thing like this. That's going to be 6.67 meters per second. How did I know it was meters per second? Well, if this is in meters, right, when we differentiate, it's going to become m over s. It becomes meters per second, and then when we differentiate again, it becomes meters over seconds squared. So these will be our units. Okay, calculate the acceleration of the train after 2 seconds. Acceleration. Remember, we had to differentiate to get to velocity, then we'll differentiate again to get to acceleration, and that will be our units there. Okay, cool. Let's differentiate this one here. So, and then that will give us a of t. Give myself a bit of space. 4 minus 2t over 3. That's going to be our acceleration. Cool. And a of 2, the acceleration at 2 seconds, is going to be 4 minus 2 times 2 over 3. Do we need a calculator for that? No. 4 over 3 is 1.3 recurring, so that's going to make it 2.67 meters per second squared. We'll do a calculator just in case. 4 minus 4 over 3. Sweet. When was the train traveling fastest? Ooh, there we go. This is some real kinematics now. Like this is useful stuff, but this is where it gets way more interesting. When is the train traveling fastest? What is fastest a measure of? Measure of velocity. So we want to find out v of t. We want to find the max velocity, right? That's when we're going to do that. So if we want to maximize v of t, that means we're just going to find out when its derivative a of t is equal to 0. Let's sort of think about that a little bit deeper. So we would have our, we'd start off, this should be enough space. Oh, it'll look prettier over here actually, a bit more white space. We'll start off with s of t, right? And s of t is a negative cubic. That's the highest power there. This power of 3 is a cubic and it's negative. So s of t is going to be a shape like this, right? And then when we look at our velocity of that, what's going to happen is it's going to be a negative parabola. And then when we get down to our acceleration in regard to time, that's going to be a negative linear line. So we're trying to find out this. We're trying to find out when the velocity is maximized. So we want to know when this one hits its max. And that is going to occur when the acceleration crosses over, or when we set acceleration equal to 0. When acceleration, see how the acceleration is going to be, it's going to be accelerating, 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 and then it will stop accelerating. And that means in turn that the velocity is going, the velocity is increasing less and less, and then finally the velocity stops increasing, and then it starts decelerating here, and that's when the velocity starts to decrease. So maximum velocity happens when acceleration is equal to 0. So let's do that. A of t equal to 0, which means 0, we'll just do it straight from here, equals 4 minus 2t over 3, and then we'll solve for that. I'm going to bring the 2t over 3 over, equals 4, 2t equals 12, and I'm going to do it over here, t equals 6. I'll do a nice little arrow, sing, boom, boom. T equals 6, what are we measuring in? 6 seconds is what we are measuring in here. When was the train traveling fastest? How, they added on a flippin' another question here. How far was the train from the station when this occurred? Well, we now know it's when t equals 6. How far is a measure of distance? So we're going to have to use our s of t. So we'll grab that from here and we'll just chuck 6 in. So we want to find out s at 6 seconds equals 2 times 6 squared minus 6 to the power of 3 over 9. And we'll use a calculator for that. S of 6, 2, 6 squared minus, we're going to make this good. We're going to go like this. We're going to go 6 to the power 3, so it's going to go power is E in dead mass, and instead of using an over, I'm just going to use divide, because your calculator actually does fractions before it does powers, I'm pretty sure. So if we use a divide, then this gets priority, and then it will do the division afterward, and that's what I want it to do. Yeah, that should work. 48. That means the distance is at 48 meters at that point. Does that make sense? At 2 meters, at 2 seconds they were 7 meters away, and then 48 meters away when they hit their max speed. Yep, that makes sense to me. Okay, when did the train return to the station? Okay. So the train's going to return to the station when the distance traveled by a train from a station is 0. So what's going to be happening here is the train, these 2 points, so the train is going to start at the station. It's going to go some distance away from... Now, where would it actually start? Oh, maybe it's somewhere around about here. Yeah, the train's going to like start. It's going to get further and further away from the station. Then it's going to start decelerating, right? We're going to get decelerating, but it's going to decelerate to the point where the velocity actually becomes negative. See down here, the velocity becomes negative. So then it's going to go back. So it's going to like start at the station, and then when this hits the same point, it'll be back at the station again. So it's going to be like hitting reverse for a while here. See how the distance away is going to be increasing, like how far away it is from the station. Then it will hit a point where it's like coming reverse and coming back to the station, right? So its velocity increases, it gets faster and faster, then it slows down, and then its velocity is going to go negative around about here, right? So because the acceleration is constantly decreasing, it decelerates the whole time until the point where it's actually going in reverse. So that explains it. So the idea is, when is s of t equal to 0? When is its distance equal to 0 meters away? And we're going to find out. It's going to be like a cool way to do this. I feel like this is not actually calculus at this point. No, it's kinematics, who cares? Okay, so it's when 0 equals 2t squared minus t cubed over 9. Right? So we can factorize out this pretty easy. 0 equals, and we can pull out a t squared. T squared 2 minus t over 9. What t squared tells us, the fact that t squared comes out, it tells us that the cubic has a kiss. It tells us that it comes in, kisses here, and then goes down like that. So we know that t squared actually tells us that. But that's like an algebra thing, right? So we actually know now that, let's make it s of t and t. We actually know from the fact that you can factorize out a t squared that this happens bang at 0. So our beginning, the train does this, and so we're just now going to try and find out where this point happens, and that's going to be told by this. So t equals 0, and that's a kiss. And then over here, let's solve this. 2 minus t over 9, where does that equal 0? It's where t over 9 equals 2, and so it is at t equals 18. So there's one at 0 and one at 18, right? When did the train return to the station? At t equals 0 seconds. Oh, shucks, no. 18 seconds. My bad. Okay. When was the train the greatest distance from the station, and how far was it from the station. Okay, so it's this point here, right? It's at the max distance. I mean, you could actually say that the train travels, like, it could go reverse from the station, like negative infinity. It actually travels infinitely far away from the station, but I'm assuming they're talking about in this range, only in the positives. Right, when this goes back to 0, we can actually just assume that the train stops and is finished at that point. So we're actually just focusing on this. So how do we find this? This is here, right, when we have our max distance, and max distance is going to happen when this parabola crosses over here, right there, right? So all we need to do is use our velocity function and find out when velocity is equal to 0. The reason being is when the velocity hits 0, it's the point when the train goes from getting further and further and further away from the station, and then it's this, when velocity becomes negative, the train is coming back home, right? So the train here leaves, and it's speeding, it's going faster and faster, it hits its max speed. It's still actually positive velocity here up until this point, and then the train is stationary, and then the train turns around. Or trains don't turn around, the train goes in reverse back to the station. Right, so it's this point here. So it's when v of t is equal to 0. Yep, when v of t equals 0, where's our formula for that? It's when 0 equals 4t minus t squared over 3. That's when 0 equals, and then we can factor out that, t 4 minus t over 3. So let's draw a picture over here this time. So this is v of t, and we know it's at the velocity is 0 at the start, maxes out, boom. So we now know from this, we can see that t equals 0, the velocity is 0, right? And that's this point here, when t equals 0. But then what's this other point? We can solve it from this other side here. So it's 0 equals 4 minus t over 3. That means t over 3, oh shucks, not on the screen. T over 3 equals 4. T equals 12 seconds. So the other point here is at 12 seconds. And yeah, that is when, so this is looking at velocity, so the train's going faster and faster and faster, but then that's when I want you guys to understand this concept that the train, its speed is actually decreasing, but it is still going forward, right? The train's still going forward, and then at this point the train is stationary because its velocity is equal to 0, and then from there onward the train is actually in reverse, right? So that is the point where it's at its furthest distance away from the station. Okay, that's page 71, done.